So let's go through our last module. Happy days, we're at the end. Sad days, we're at the end. We've learned a lot, but we've finally built up to where we were trying to get to, where we can actually apply this to some real quantum mechanics. So there is an implementation of Hartree-Fock, the quantum chemistry calculation algorithm, in Julia. It was written by a previous Iowa State graduate student in my group named David Poole. It's also the project that I currently work on, hence one of the reasons why we're using Julia. We will use it to explore the H2 atom at varying internuclear distances, and our goal is to try to find the internuclear distance that's at equilibrium, so the lowest energy value, which we will hopefully be able to do in our final project. One thing that will be helpful to do this will be able to plot some data. So we will use the Julia package called plots.jl. So this is just going to plot some random data. Keep running this, it's going to do random output. But essentially you have the plot function, you pass it some data, XY data. You can title it, give it an X and Y label. If you see this exclamation point at the end of any method, that's a Julia best practice or pattern or way of telling somebody, the other people who are using your code, that you're going to modify the thing that's being passed in or already in existence. So we're modifying the plot object that we've already created. Just a thing to watch out for. This is probably a little bit more clear. So we have an array of X data and an array of Y data that have the same length. We're passing it into our plot as X and Y, title and date, or sorry, title and label, and a XY plot as we would expect with, you know, a slope of 2. We can also plot functions, so we create a function that's e of negative x. We pass in a range of values we want to plot that over, and it will plot it for us. We can also plot multiple things, so now we have plot versus plot exclamation point, which will use the same plot and create 2 lines. So one, we have e to the negative x and e to the negative 2x. So you can see there, you can kind of, your imagination can run wild and do whatever it is that you want to do with that. So last one, to be able to save. So instead of printing it out to the Julia REPL, or not REPL, this is a Jupyter Notebook, we can save the file. So this saved it over here. Yeah, that is how you use plots. So that is our last really functional thing that we're going to learn in this programming tutorial. So good work getting up to this point. Now we're going to bring it all together to do some Julia Chem. So I kind of introduced Julia Chem at the beginning, but here's how you use it. One note, unless you're running on a Linux machine, Julia Chem is not going to work for you. So that's why we're using Google Colab. The Jupyter Hub, Binder Hub, or whatever I was using also didn't work for Julia Chem. So that's why we had to switch technologies in the middle. See the previous video in the series on how to get that all set up and make sure it's working. But Julia Chem at a high level, the first thing you do is initialize it, do the calls you want to do with it, and then finalize. So that's just a very common pattern. So Julia Chem is going to set up some functionality and load some data beforehand. It works with input files, so you're going to pass in, one passes in a JSON file to it with the various information, and I can show you what one of these looks like. Just open it like this. So you've got your molecule information, the geometry, so where are those molecules in space. So an easier way to think about it, so it's first 3, second 3 correspond to this H versus this H. Driver, just telling it what we're trying to do. Our basis set, so our functions, so if we were thinking in terms of H atom, what you call it, orbitals. So a basis set are like orbitals for computational chemistry, so they're functions that can be used in a combination to create molecular orbitals that describe the electron densities and clouds of a molecule. You don't need to worry too much about that, but you may have heard a little bit about that in class, maybe talking about minimal basis sets. So this is a minimal basis set. Don't worry too much about this. All this stuff has been abstracted away from you. You don't need to worry too much about it, but if you're interested, this is the schema that we're using, so the way that lots of programs out there are doing their input files so that more programs can be used interoperably, meaning they can be used together using the same kinds of inputs and outputs. But anyway, the output, you're going to see it returns a dictionary of values. So we talked about dictionaries in the last video a little bit. I think we did, maybe we didn't. Regardless, yeah, we talked about it. So anyway, again, all this stuff has been abstracted away from you. So I have this runner class, and it's in that Jupyter notebook that basically does all of the Julia Chem stuff for you. You just need to call them in the right order and use this, and it'll create an input file for you based on the radius that you pass in. So don't worry about it too much. What you need to focus on is creating a script that uses that functionality that I have in the Hartree-Fock runner that's in the Google Colab file. So you are trying to investigate and find the lowest energy you can get at the radius. So you're going to need to play around with it, maybe run it a few times just to see some energies that you get, or run it for a range of values. Then you're going to need to, once you kind of understand where the low value is, you can do a sweep around it and plot. So get some, you want to get some that are, shorter distances and longer distances than the equilibrium bond, so we can see that whole curve, the dissociation curve. And then we also want to, in our script, print out in some clean way using println, what have you, the minimum energy and the internuclear distance at equilibrium. So where you find the minimum energy, keep track of that value and the internuclear distance that you passed in. So one note, it's not going to be the exact value that you might find in literature. It depends on what basis set, but the shape of the curve should be the same as everything that you see in a textbook. So try it out, plot it, see what you get. Some general advice, don't start too close to 0. It will make the plot look weird because as the distance goes to 0, the energy goes to infinity. So start a little bit just before, just get a few values before the equilibrium value, so you get that nice steep curve on the left, but it doesn't go too high up and skew what you want to see on the curve. Don't go too far past the equilibrium because it's just going to be a flat, kind of it flattens off at a certain value, relatively speaking to the left side of the curve anyway. It's kind of actually more linear going straight up, but and then look at the textbook and literature plots out there. It gives you some guidance on good ranges to use. Pay attention to your units. So we're passing in atomic units of length, and it's returning atomic units of energy, so Hartrees, and atomic units, so Bohrs. So yeah, if you have any questions on that, let me know. Once again, tried to have a nice short video so you can spend more time coding on this. As I said, let me know if you have any trouble, and I can help you in any way I can. Happy to help. Thank you for going through this process. I've enjoyed it immensely teaching it. I hope you guys have taken something out of it, and will continue to learn more code as you go forward. Or if not, it was at least enjoyable to do it, and failing that, the extra credit was worth it. So thanks for the feedback. Thank you for doing it, and let me know if there's anything I can do to improve it. I already have some ideas of what I can do in future semesters, but your guys' opinions of this will be especially helpful to me. So feel free to, in the feedback for the final module, provide whatever feedback you think would be relevant kind of to the whole process. Yeah, so thanks.